So we have finally reached the part where we are assembling things together and finally making the VIT. In the last video, we discussed how self-attention works and we wrote the code for it and we saw how the outputs are given. So one thing to keep in mind is that we essentially give the output layer, as in the output of the last layer, as the first index or the zeroth index, and the attention scores are given after that. So one onwards is attention score. Now, let's try to implement the VAT block. Pretty straightforward. We can see the diagram here. There's a layer normalization. There's a multi-head attention, which we just defined in the previous video. There's one residual connection, which connects the input to the output of the multi-head attention. Then there's a layer normalization and there's an MLP. So what is this MLP? This MLP is pretty simple. All the MLP does is it upsamples the output to a certain dimension, to a higher dimension, and then brings it back down to the original dimension and gives it as an output. And then again, there's another residual block which connects the output of the concatenated output again with another skip connection. Now, let's look at the code. Of course, the code is pretty straightforward. VIT block inherited from an n.dot module. We have multi-head attention, which is VIT self-attention, which is what we have defined in the previous video, that is in this class. Now, we have two layer normalizations, so we declare both of them separately since they need to be backpropagated separately. For the MLP, we have dense layer 1, which takes hidden dimensions and upsamples it to some upsample MLP dimension, which we can define in our config. And in case you are wondering what the config is, I have the config right here, which I used. You can change the numbers, obviously, and use whatever values you want, but these are the values I set. And this is the config file which I give during training or during model initialization or anything. Now, there's another MLP dense layer 2 where it brings it back from the upsample MLP dimension to the original hidden dimension. And then there's a dropout for experimental reasons. Now, in the forward function, we have an image embedding which comes in. We know that we have declared the patch embeddings and all that. And finally, we get the final embedding. Simple, we just implement this diagram here. So starting with a layer normalization of the input, and then the output of that is normalized embedding, goes to multi-head self-attention, and we get the block outputs. Now, we know that the first one is, or the zeroth index is the output, and 1 onwards is the probability. So if we give return scores as 2, then this value will exist. Otherwise, it will not exist. Now, residual connection 1 is image embedding plus attention output layer. Attention output layer is this, and image embedding is the input. That is this residual connection which we have over here. Now, MLP upsample output is we pass it through dense layer 1 and then we have an activation. So the activation we use here is JLU, and this is the common activation used across VIT. That's what the author suggested, and that's what turns out to be the best activation function in our case. You can Google up the formula. It's pretty simple. It's just an advanced version of ReLU where you have a small bump in the beginning instead of a sharp curve like ReLU. Now, MLP downsample is where you bring it back down to the hidden dimension and then we apply a dropout. We apply the next residual connection, which is MLP dropout plus residual connection 1. That is this one. So this residual connection gets again skip connected to the output. Now, final output is residual connection 2, that is this, and attention probabilities. And we can give the final output. So attention probabilities exists if the return score was given as true. And that is the key thing to remember here. This is one VIT block. Now, when we need to make an encoder, we need to set multiple number of blocks like this. And in the paper, we can see L number of blocks, for example. So I set a value in my config file called number of attention blocks. That is this one. So for example, I set it as 12. So all we need to do is that we create a module list where we create n number of VIT blocks. That is whatever this number was. I've set it as 12. So for underscore in range 12, so the for loop runs 12 times. So we declare 12 VIT blocks in a list, and each of these blocks will take an input, pass an output to the next block, that will be the new input. Now that gives an output, and so on and so forth. This goes back to back. In the forward function, we have input embeddings, we have return score as another input, and output hidden states as another input. So these are all again meta inputs where we can choose to return certain meta values or certain metadata which might be important for our experimentation. So we declare an all hidden states tuple which is empty in the beginning. and all attention scores again an empty tuple. Now for I comma layer in enumerate self dot layers, so we go through these self dot layers, we go through each layer of that, and we pass the current hidden state to that layer. So in the beginning, the current hidden state is equal to the input, but after each block of ViT gets processed, we can essentially replace that. Now we can see that here current hidden state is equal to layer output of 0. So we, as soon as we pass a ViT block, we can immediately take that output and replace current hidden state with that. If return scores is true, we can attach the scores to the output, and if output hidden states is true, then we can attach that to the output as well. And finally, we can return a tuple depending on whatever the user chooses to keep true. But regardless of what they choose to keep true, we will give the final output, that is current hidden state, so which will be replaced by the output of the last layer in this for loop. Now, we need to do one more thing before we go to the model, that is the pooling layer. So pooling layer is pretty straightforward. We get an output finally at the end of the model where we take out the classification token alone instead of the other tokens available. We take out the classification token alone, pass that to an MLP layer for classification. So let's see how we do that. So we have a dense which is declared here as n.linear of hidden dimensions and output of hidden dimensions. So this pooling layer will occur right here where the output is coming out of the model, but it is still not the MLP for classification yet. It is a refinement point where we are pooling the features. So this layer does not change the dimension of the output at all because the incoming dimension is hidden dimension and the output is also hidden dimension. The activation we use here is tan h. Again, that is experimental, and of course, that's what the authors suggested. In the forward function, what we do is we get the hidden state, that is the last output of the, let's say, the 12th block of ViT in our case. The classification embedding will be hidden state colon comma 0. This is the first index of the output, right? And this is for batches, obviously, which is why it's left as colon so that we take all the batches. Now, the pooled output is self.dense of class embedding. That is this one. So essentially, it's just a refinement layer where the output remains of the same dimension. It just gets refined there. And pooled activation is self.activation of pooled output. So we pass it through TANH, and whatever output is, we just return that. ViT model is where we assemble everything together and we finally get somewhere. So if you look at this, it is a combination of everything we have created till now over the different parts. ViT model, self-dot embedding is ViT input embedding, which is the first thing which we made. Encoder is ViT encoder. We have a layer normalization and we have a pooler. Now, in the forward function, it's as straightforward as it gets. Image embeddings is self-dot embedding of input image. We get those embeddings, pass them to an encoder, get the encoder output, take the first index of the encoder output, since that is the output and the others are probably attention scores and all the hidden states and stuff. Now, attention output norm is when we pass this output to a layer normalization, and then what we do is take the attention output norm, pass that through the pooling function which we just created, and take the pooled output and return that. Now, we can either return the output norm or we can return the pooled output. I just return both so that it's versatile enough to output whatever you need. And of course, we can have the other outputs if they exist. For example, if we have said return scores is true, then of course we'll have more outputs here. So we just put 1 and colon so that if anything exists, it obviously comes into play, right? So that is pretty much it for this video. We have finally made the model. In the next part, we'll see how we can use this backbone for classification. Actually, calling this backbone is not really fair. This is pretty much the model. We just have an MLP to put it on top, and essentially it's a classification model. But in the next video, we'll look at that. We'll look at a data loader, and we'll look at a simple training code which can train this model on, let's say, CIFAR 10 or a simple data set like that. So that's pretty much it for this video.